When researchers are working on artificial intelligence, one of the strategies they will use is to mimic biological systems, and in particular, humans, since we have, the best learning that we are aware of. In this case, the paper you see before you is on Hindsight Experience Replay, where the authors have attempted to use the phenomenon of hindsight to improve learning in robotic continuous control systems. The basic idea is that we start off every episode with some goal in mind. In this case, it's a robot that is attempting to push an object towards a goal, or pick it up and put it at the goal, or even stack some objects, or even just take its gripper and move it to a target location. So it has some goal described by XYZ coordinates, and it compares its success or lack thereof to that desired goal. Now, it turns out that by carefully selecting goals in hindsight, we can actually improve the performance of our agent quite significantly. Specifically, what you can do, and what we're going to implement in this video, is something called the final strategy, where we're going to say, okay, you didn't get the box in the exact spot you were looking for, but you did get it in some specific part of the table. Suppose you had started that episode trying to actually move the box to that position on the table. Then you would have been successful. And it stands to reason, if you can back out how you were successful in getting the box from the starting position to the ending position on the table, you can develop a realistic model of the world and use that to move the box to any arbitrary position on the table. The basic idea here is that our rewards are sparse because we most often don't get the box where we want it to go, but we can re-engineer our rewards such that we do get a viable learning signal for our agent. And we can just say, wherever you ended up, that's perfectly fine. Figure out how you got there, and then use that to build a model of how you move your motors around, how you move the box around, and how the world works. And it turns out that this works remarkably well. And we're going to demonstrate that today in this video using some starter code I've provided for you with a twin delayed deep deterministic policy gradient agent. So what you see here is the paper from Hindsight Experience Replay, and we're looking at the algorithm itself. So the idea is we start off with some off policy algorithm, deep Q learning, DDPG, a few other examples, and then a strategy for sampling, goals for replay. Now this could be totally uniform sampling, this could be prioritized sampling, this could be any other way of sampling memories. We're going to use uniform sampling, where we're going to be substituting goals over the course of our learning. And then you have a reward function that maps your state space to some achieved and desired goal yielding a reward. So in this case, we're going to be dealing with environments in which the agent gets a reward of -1 in every time step, except for the step where it is successful, in which case it gets a reward of 0. So it's going to try to minimize that negative reward or reach the goal as quickly as possible. So then you're going to iterate over the steps of an episode, sample some goal and initial state. This is critical. You want to make sure that your initial state doesn't line up to your goal state. So those are two separate things. You don't start off the episode successful. Otherwise, the agent isn't going to learn anything. And then iterate over the course of the episode by selecting actions, executing them, and observing new states. And then at the end of the episode, what you're going to do is you're going to go over all of these states that you encountered in that episode and store that transition in your memory. And then what you're going to do is sample an additional set of goals for replay. So you're going to store what you actually did along with the original desired goal, and then you're going to sample some additional goal that you actually achieved through the episode and store that as the desired goal instead of the original desired goal. So I hope that makes sense. And there are multiple different strategies, and this is really the magic of Hindsight Experience Replay, is that you have a number of different strategies for selecting that actual final goal for this particular step. What we're going to do is we're going to take the final step of the episode as the hindsight goal, and then we're going to recompute our reward based on that. So the final step will always have a reward of 0 because wherever you ended up was where you intended to go in our hindsight example, and so you get a reward of 0. And then of course, you do the learning stuff with sampling the mini batch and performs optimization on your agent. So to get a feel for what type of activities this is applicable to, you have this robotic arm here where there is a box and a goal, and it's trying to move the box to the particular goal. Now it can do it by pushing. It can just kind of nudge the box all along. It can slide it where it gives it an impulse and the box slides. So it has to learn something about the physics of sliding. So how much friction the table has, how much mass the box has, so on and so forth, as well as picking something up and placing it somewhere else. We are going to use a much more simplified environment, just reach, the Panda reach environment, where the agent is going to attempt to put its claw at a specific point on the table and get a reward based on how close it gets to that goal. Reason being is that it's going to learn much quicker, it simulates much faster, so it's going to get you guys results much more quickly. Of course, you can just substitute out the environment string and you'll be off to the races with these other environments. Now, in this paper, they used DDPG, they used a multi-threaded version, which we're not going to do. So what they did is they had many different environments and they average parameters over the different agents and re-download them to each of the agents. It's overly complex. We don't really need to do it for the simple environment and for the purposes of learning what Hindsight Experience Replay is. It's really superfluous. It's not something we have to do, so we're going to skip that. I covered in my course on my Neural Net Academy. I show you how to do all of this from start to finish, but for the purposes of YouTube, we're going to get just the essential concept of what's going on. So this is the basic idea, and you can take a look at the performance here where you have pushing, sliding, and pick and place. So the key thing is that the reddish pink type curve is deep deterministic policy gradients plus Hindsight Experience Replay, and you can see it achieves a high success rate much more quickly. The dashed line here at the bottom, pegged along 0%, is just plain DDPG, as well as DDPG plus count-based exploration. So if you're not familiar, count-based exploration is just a type of curiosity where we say you get some reward in proportion to how often or how infrequently you visit a certain set of states. And then you can see this similar trend in other environments. Sliding and pick and place have similar behaviors. And then they experiment with single goals, multiple goals, picking some k equals 4, 8, 12, whatever number of goals, and they go in great detail in how you pick the goals, k random states from the future from your current step, k random states from the same episode, and then just a random state encountered so far during the whole training procedure. So there's a bunch of different schemes that we implement in the course, but we're going to focus on the final goal and just the case of a single threaded agent. And we're not going to use DDPG, we're going to use twin delayed deep deterministic policy gradients. So let's take a look at the environment we want to use. They use Mujoko. We're not going to use that because I am permanently frozen on Gym version 0.18 because that was the last version where they incorporated the Atari licensing. In later versions, they incorporate Mujoko licensing, which is cool. So, you know, it's a bit of a trade-off. I'm going to use an open source version of these environments, and I'm going to show that to you presently. So you can see here, this is a library called Panda-gym. I am running the 2.0 version. This is currently on version 3.0, I think. It has instructions for installing, but the basic idea is that it has pretty much all of those Mujoko environments and then some. So you have the Panda Reach. Let me see if I can zoom in for you guys, where the robotic arm is attempting to reach the spot on the table. Kind of difficult to see, but you can see it as a little green speckle there in the back. And then the Panda Push, where it's trying to push the green box towards the target position, sliding, picking in place, even stacking and flipping a box where the box has a preferred orientation. So there's a bunch of different environments to play around with, and it has good instructions for installation. So this is a great place for you guys to start. So I would recommend getting this and as well as downloading my starter code from my provided GIST link in the description below, because you don't want to have to write all of the code. So the reason is that this environment returns data in a format that's a little bit different than what you might expect. It returns it as a dictionary instead of an array. So we'll take a look at that here in a second. Okay, so here we are in our trusty terminal. Let's take a look at the versions of packages I'm using, because this is the #1 way for your results to differ from mine, or rather for your results to not even be achievable because the code doesn't execute because some change has been made, most often to NumPy or PyTorch, that breaks my code. So I'm running Torch 1.7.0. Let's take a look at what version of Gym I am running. Sorry, that's pip list grep gym. I'm running gym version 0.18.3 and Panda-gym 2.0.0. And then let's just take a look at NumPy as well, because this breaks a lot. With the setting array element with the sequence error is directly related to NumPy. And we get version 1.21.5. And as an aside, I am working on fixing that stuff. It's just a bit overwhelming to have to go back over basically dozens of implementations and try to bring them all up to speed with modern standards. So that's a bit of an issue. That's why I've started going over package versions in the beginning of the video, because that will eliminate many problems. Also, one thing I want to point out is that I'm running the code right now on my machine. So in this window, we're running the Panda Reach environment with Hindsight Experience Replay using TD3, and after a while it achieves an average success score of 100%. In contrast, TD3 by itself without Hindsight Experience Replay doesn't achieve any success in the testing phase. So let's take a look at some of the starter code I have provided for you. So I have an agent, so let's take a look at the agent. This is TD3. If you've taken any of my courses, either on Udemy or through my academy, this will be pretty familiar to you. I've changed a few things around, but nothing substantive. The main thing that's different is that the agent doesn't have a memory. The agent takes in memories from the main loop and then unpacks them where they're assumed to be, a list of stuff. And then what's critical here is that we're going to be concatenating states and goals. So the state and the goal become one vector. This relies on the paper on universal value function approximation. I briefly touch on that in the course, but the basic idea is that we're just going to bolt the we're going to concatenate the states and the goals, kind of bolt them together and pass that as one input to our deep neural network. And so the agent will learn to correlate, the neural networks will learn to correlate two different parts of that vector with where it ended up and where it wants to go. And then you have the typical TD3 learning algorithm where we update the actor and critic with varying frequencies. We delay the learning of the actor in particular. Other thing that comes from the Hindsight Experience Replay is clamping your target in this limit range, and it's just in the range of -1 over 1 minus self.gamma. So it makes sure that your target doesn't become too large, where you're feeding a large number into your deep neural network, causing it to explode or vanish or something like that. So it's there to ensure that the learning actually converges to something reasonable. And then of course copying parameters and saving models. We also have an episode file. So what this does is this comes directly from the multi-threaded implementation, which we aren't doing, we're just doing single-threaded. But the observation space is actually a dictionary where you're served up the observation space as a dictionary where you have the keys that correspond to the observation, the achieved and desired goals. And so I extract those, convert them into slices, and then use that to get actual observations, because in my environment, I use an environment wrapper to convert this dictionary into a array. Just here, let me show you that real quick. So if we take a look at wrappers, you see that I convert the observation from a dictionary to a NumPy array. That's just done for simplicity, so that we don't have to constantly reference the keys of a dictionary. We can just use these slices. We can say, okay, we know that the observation space is whatever, 4 elements, the achieved goal is 3 elements, the desired goal is 3 elements, so the whole thing is 10 elements long. So 0 to 3 gives you your observation, 4 to 6 gives you your achieved goal, and then 7 to 9 gives you your desired goal. So you can use slices instead of dictionaries. It's just an easier way of handling things. And then we play episodes in much the exact same way. We just have to take into account the fact that our observation is a vector of length that's much longer than the actual observation because it includes the goals itself. So we dereference all of those, and over the course of each episode we keep track of everything within that episode, all the states, new states, rewards, actions, dones, desired and achieved goals. I have achieved goal and achieved goal underscore because at each time step you get an achieved goal. So the AG corresponds to the achieved goal for the state. AG underscore corresponds to the achieved goal for the new state that comes about after the agent takes its action. And then, of course, you do the typical setting the new achieved goal and new observation, the current achieved goal and current goal to, and current observation to the new observation. You get what I'm trying to say. And then if we're not evaluating, then you want to store the episode. So if you're in an evaluation phase where you're testing its performance, you don't want to keep track of that stuff. And then each episode has a success marker, and then we can return the total score and success. So this plays a single episode. It's an episode worker. If we take a look at the main function, we train over epochs and cycles. This is how they handle it in the paper. So within each epoch they have 16 cycles, and there's 50 episodes per cycle. So an epoch is 50 times 16 or 800 episodes. And then they do 40 updates per epoch. So that's 40 steps of your gradient descent algorithm. So we sample the memory and learn. And then we update our network parameters after each set of learning. And then you have a sequence of test episodes where you set the evaluate flag to true, where we're not going to use any noise. We're just going to use the pure deterministic output of our deep neural network, of our actor, to get the actual action and calculate the averages. Oh, and I do have this MPI world rank 0 here. Let's see, let us delete this because we're not using MPI. That won't, actually wouldn't have broken anything, I don't think. Get rid of that. Changing stuff on the fly sometimes doesn't work out, but that is vestigial from using MPI in the actual course. I just forgot to delete that line. So this train function handles calling the episode worker to play an episode over the course of epochs and cycles. And then we have our main function where we define our environment. We make our environment and flatten the dictionary into an array. I have it set up to either use Hindsight Experience Replay or not, a batch size, a max size for your memory, so on and so forth. All the typical stuff associated with playing an episode. So let's right quit out of there. And then you can see, let's take a look at the performance. So as of the 18th epoch of testing, the Hindsight Experience Replay agent has pegged the success rate at 100%. And as of the 20th epoch, the vanilla twin delayed deep deterministic policy gradient agent is still struggling and has had absolutely no success. Okay, so that proves the validity of TD3 even in a simple environment like reaching from the starting position to a specified position on the table. So let's take a look at our Hindsight Experience Replay file. This is a very typical memory in the way that I write things, where we have NumPy arrays for what we want to store. We're going to be using states, new states, actions, rewards, dones, desired goals, which is the initial desired goal at the beginning of the episode, the achieved goal. So every time step an achieved goal is wherever the either the gripper or the box ended up. And then of course the achieved goal underscore corresponds to the achieved goal after the agent has taken an action within a step of an episode. And then our typical function to store a memory, get your first available position and store everything and increment your memory counter. The store episode function is the one we want to write in this video. And then we're going to do a normal memory sampling where we use uniform random sampling with no replace, so we don't repeat any memories. And then we also have our ready function. And keep in mind, we're not returning achieved goals, just desired goals. So you want the agent to append the desired goal where it wanted to go to the current state of the environment. So let's write our store episode function so that we can implement Hindsight Experience Replay. Okay, so we're passed in a number of things. We're passed in some episode memory and a use Hindsight flag. So let's unpack our episode memory. So we have states, actions, rewards, new states, terminal flags, desired goals, achieved goals, and new achieved goals from our episode memory. So then we're going to have some set of hindsight goals. In this case, we just want the final goal from the episode, so the final achieved goal. So we're going to say hindsight goals equals a list of list elements ag minus 1 times the length of ag underscore. So what we're going to do is we're going to iterate over every step in the episode and set that desired goal to the achieved goal from the final state of the episode. So what we say is for s, or excuse me, idx and s in enumerate states. Let's put that on a new line. We're going to say self.store memory s actions idx rewards idx states underscore idx and done's idx dg idx ag idx and ag underscore idx. And then if we're using hindsight, then what we want to do is say for goal in hindsight goals sub idx, the reward equals self.reward function ag underscore idx and goal, and you have to pass in an empty dictionary. So all this reward function does is it's a numpy function that does like an all close between the achieved goal and the desired goal to see if they're close enough within some tolerance. And if it is, it returns a reward of 0, otherwise a reward of -1. Then we say self.store memory s actions idx rewards idx states underscore idx, basically the same thing we did above. Oh, sorry, it should be reward, not rewards. I was looking at my cheat sheet. I'm like, the length of these lines don't match. That doesn't make sense. We don't want to save the reward the agent achieved in the episode. We want to save the new reward that we've just calculated. And then say done's goal ag idx ag underscore idx. And that is it for our store episode function. Of course, it should be hindsight goals. Okay, then we can right quit out of that. And then moment of truth is should function unless the MPI world rank removal broke something. I can run, let's take a look at main and say use hindsight should be true. Okay, now let's try that and see if we've broken anything in the process. And of course I have results still running from the other two tests I'm doing. So just to remind you, this is with hindsight and this is without. No success at all without hindsight. And this is running, so it didn't break. And it does take a long time to run. When you use multi-threading, it's much faster, but the single-threaded implementation is rather slow. So I hope that was helpful. That is Hindsight Experience Replay in a nutshell. The only thing you really have to change is how you select those hindsight goals. We just use the final step from the episode. You can select them at random. You can select some states in the future from a current episode, you know, some state that occurred after whatever state you're looking at in that on that outer loop. There's any number of different ways that you can sample it. And in the course, I cover all of these things, but I wanted to give you guys a very easy and simple, gentle introduction to the topic of Hindsight Experience Replay. Let's see if this, nope, still doesn't learn. Okay. All right, so that is all I have for that. For more deep reinforcement learning tutorials, you know what to do. Make sure to subscribe. Any questions or comments, leave them down below, and I'll see you in the next episode.